We will start at 9:30, so we still have 8 minutes to wait. So we will start the online lecture at 9:30. So we still have 5 minutes to wait. Okay, so good morning, everyone. So welcome you to study this course, which is about the microprocessor system. Uh, Today is a public holiday. This is why we are going to do the lecture online. But anyway, this lecture will be recorded, right? For those of you who could not attend the lecture, you can find your own time to watch the recorded lecture. Okay, so today we are going to quickly go through the course introduction, and then the key takeaway from today's study is about lecture one. Okay, so lecture one will be the main focus of today's lecture. Okay, so let's start with a quick introduction about this course. Okay, uh, inside the NTU Learn, you should be able to locate all the lecture slide, and in particular, you should be able to find this teaching plan. Okay, so basically, this course will be taught by two instructors. Okay, so my name is Xie Min, and another instructor is Dr. John Han. So I will teach the first part, which will last for 6 weeks. Then subsequently, Dr. John Han will take over for the second part of this course. Okay. And if you look at the schedule, every week we have a 2 hour lecture and 2 hour of lab session. But this 2 hour lab session has been allocated to two groups. Then from the viewpoint of your study, you only spend 1 hour for the lab session. Okay. But for this course, we allocate 2 hours for lab session because 1 hour for each group. Okay. So you know the location for lecture LT6 and the location for lab session is inside robotics and the learning lab, right? Okay. And you look the schedule for the first 6 months, first 6 weeks. So I will cover basically the software part of this course. Then for the remaining 7 weeks, 7 teaching weeks, Dr. John Han will cover the hardware aspect of this course. Okay. But for assessment, there will be two CA and one final exam. So CA will account for 40% and the final exam will account for 60%. Okay. And for my part, the CA will be consist of 10 MCQ, right? So it is quite straightforward MCQ, not so difficult, right? Okay. And for reference book, okay, reading material, you just follow this guideline, right? So we have this down two book plus one reference material, okay? So all this you can find from the NTU library, or for the reference material, then you from the NTU Learn, right? The inside the folder, or eventually inside the folder in the lab when you do the practice, because once you log in and everything is there, you should not worry about any reference material, etc. Okay, so I guess you know NTU's mission, right? Number one is education, or number two is research and innovation enterprise. Okay, we also want NTU to be the house of a talent, right? And also the hub of a global impact, etc. Okay, so these are the four mission of NTU. And then for you, you also need to remember your mission as a MAE student. Okay, so this is a basic version of a mission statement. Pay attention to the keyword of design, machine, controllable behavior, intelligent way. Okay, so once you know this mission statement, immediately you understand this course is extremely important for you to fulfill your mission. Without the knowledge and the skill learned from this course, it is impossible for you to fulfill your mission. Later on, you will see why. Okay, then how to fulfill your mission? Then you look at this slide, you see we have an inner automation or inner control loop. We also have an outer autonomy or AI loop. Okay, so inside the inner control loop, do you see the control module? Then behind the control module, the hardware support should be microcontroller. So therefore, you understand, without the knowledge and the skill learned from this course, it is impossible for you to implement the inner loop. So without the inner loop, how are you going to implement the outer loop, which is the AI loop? Okay, today AI is very, very hot topics. Okay, if you want to venture into the study of AI, it is necessary for you to understand what is a control loop. Because without knowing what is control loop, how are you going to understand what is AI loop? Okay, so follow the guideline. Okay, shown in this slide, then you know how to fulfill your mission and prioritize the study of courses. Okay, and for my background, okay, I just quickly go through. My role is to help you, right, to learn this course and okay, to score or to earn the AU, etc., to be resourceful, skillful, etc. Right? Okay, and this slide summarizes my background. Then from this slide, then you know, okay, my research focus is on robotics, AI. I teach robotics, sensor, microcontroller, AI courses, etc. Right? And this is my basic research. My basic research is focused on AI. And pay attention, okay? Today, there's a lot of speculation about the fake AI. For those of you, if you are keen to venture into the study of AI, you must know the difference between fake AI and the authentic AI, okay? Then we can apply AI into two interesting platforms. One is a humanoid robot, right? Today also in the media, this is also very, very hot topics, right? So a lot of companies venture into the development, design, and development of a humanoid robot. This slide showing you the prototype that we have developed, right? By the team under my supervision, right? From small humanoid robot all the way to full-size humanoid robot. The second interesting platform for you to apply AI and also the microcontroller is autonomous vehicle, right? And or driverless car, etc. Okay, and today we have this Robot X challenge, which is to demonstrate autonomous capability by surface vehicle, water surface vehicle, right? So NTU has a team, right, to which participate to this Robot X challenge. I serve as a technical advisor to NTU team. Okay, for those of you, if you are keen in this platform, you can join NTU's RoboX team, right? Okay. And the key breakthrough from my research include XI coordination. And then you know hand-eye coordination is very, very impressive behavior, which could be demonstrated by a human being. Then what is the working principle behind it? So we have discovered this working principle in year 1997, okay? Second breakthrough is about the image understanding, right? We are able to visualize three-dimensional model, okay, when we see a two-dimensional image, right? Then what is the working principle behind such a mental capability? And the third breakthrough is about the large knowledge model. Today, there's a lot of speculation about the large language model. Actually, large language model is a misleading terminology. Language is a tool for us to use, right? So what we need to do is a large knowledge model. Okay, this is just for you to know. Then this slide showing you some real demonstration with the use of our prototype of a humanoid robot, right? Okay, so it's just for you to know. And this is an international cooperation for autonomous vehicle. And okay, I can skip this. We can also demonstrate it a bit, right? Okay. Then this is a publicity material, right? Used by the school to attract researchers, right? To join our school. Okay. Then I quickly go through this introduction of microprocessor system. Okay, so you can spend time to read. Okay, and I just quickly go through. We have a two instructor just now I already mentioned. Okay, and you know already. Okay, so then you need to know why do you need to study microcontroller. Okay, if you just focus on the machine, the keyword of the machine, machine must have a body, machine must have a brain, machine must have a mind. Okay, so without the body, brain, and the mind, it is difficult for you to design, construct a machine. Okay, then what is the brain of a machine? Answer is what? Microcontroller, right? Then what is the mind of a microcontroller, a machine? Basically, it's an operating system or software which could run inside the microcontroller. Okay, so therefore, immediately you understand, all right? This course serve as a foundation for you to understand what is a machine's brain and how to develop machine's mind, right? This gives you the foundation for you to venture into the further study of AI, or eventually it depends, right? The design of the brain. Okay, maybe it's too challenging for you to design machine's brain. Okay, and if you look at the human history, the evolution, today we are in the era of internet integrated society, and we are entering AI integrated society. Then after that, we will see the emergence of robot integrated society. Okay, so immediately you see the relevance of this course, all right, which is in line with the historic trend in our modern society. Okay, so this is also for you to know the difference between philosophy and science. Okay, why I showing you this slide? This is uh, to ask you to pay attention to language. Philosophy means explanation of the truth with the use of natural language. Now you see the terminology natural language. Then what is the science? Science is a philosophy plus a technical language and eventually programming language. So this slide asks you to pay attention to human language. Human language include natural language, technical language. Technical language means mathematics, and eventually programming language, because we need to translate the truth from natural language to technical language, then technical language to programming language. Okay? In this way, the machine can help us to undertake certain mental activity, right? So pay attention to the language, because for the study of this course, language is extremely important. In particular, it is the use of a programming language. So without the use of a programming language, then it's impossible for you to study this course. Okay, so you pay attention to the language. Then what is the history of inventing computer? So you can search the story in the internet, because we have our ancestor has gone through the invention of a manually operated computer and the mechanically driven computer, and all the way to today's version, which is electronically driven computer. So today, our computer are electronic computer or electronic brain, okay? And inside we have a data flow. This is another very important terminology. Okay, it is a challenge for our school student to learn this course, because you are lack of a certain background knowledge about the computer science, but not too much. So from today, you try to slowly pay attention to data. What is the data? Data means digital signal. Then what is a signal? I guess you know lah. Okay, when you design a machine, you will pay attention to energy flow, material flow, and the signal flow, right? So then what is the data? Digital version of a signal. That is a data. Okay. So then from now on, A in another flow. That is a data flow. Okay. Remember data flow. Then it will help you to better understand the concept that you are going to learn from this course. Okay. So remember we have energy flow, material flow, signal flow, and the data flow. Okay. So this course basically is for you to understand how to produce a data flow, right? And how to control the data flow, and how to modify the data during the flow of the data. Let's say, if you want to summarize what is the key takeaway from the study of this course, answer is what? To know how to produce, how to control data flow, okay? During which you are able to modify the data. That's it, all right? Okay, then how to do that? You need to spend 1 semester to understand this achievement of a key takeaway. Okay, clear? And then what is the history of inventing electronic computer? Because today we never use manually operated computer or mechanically operated computer, right? Because they are not easy to do the programming. Okay, so this is why today the popular computer are electronic computer. Then you need to know, right? When was the first electronic computer invented, right? So then you will see it was invented in year 1945 due to a military project, because this project was funded by the defense ministry in USA, DARPA, right? Okay, and then subsequently, this electronic computer has gone through 4 generations. Then you may want to know what will be the 5th generation of electronic computer. Ask this question, okay? So we have already gone through 4 generations, okay? So that's about the short history. Then you may want to know what is a microprocessor. Just now I mentioned, if you leverage on the terminology that you are familiar with, which is the energy flow, material flow, signal flow, then you can define microprocessor system with data flow. Microprocessor system is, you can say, is a device which allow us to generate, create, control data flow. That's it, right? And here you see undertake arithmetic operation, undertake logic operation. Basically is to modify the data during the data flow. Interface with external device basically is to to flow in data, flow out data, right? Because this is the definition in the textbook. By use the definition just now given to you, that means our own definition, which leverage on the terminology familiar to you, right? So microprocessor system is a device which allow you to create data flow, to control data flow, to modify data during the flow of data. That's it, right? Create data flow, control data flow, modify data during the flow of the data. That's it, right? Think in that way, then your life is easier, right? Clear? And why microcontroller is so important? Just now I already mentioned, any machine need to have a brain, right? Without the brain, then you cannot call it as a machine. Then the device for us to use, which could serve as a machine's brain, is a microcontroller, right? So this is one way to understand the necessity of having microprocessor. Another way to understand is about the IoT, Internet of the Things, because today we are living in the era of internet integrated society. Then from this viewpoint, everything is IoT, Internet of Things. Then inside IoT, we have three basic devices. Number one is a processor. Number two is a sensor. Number three is an actuator. Now you see, processor, sensor, actuator are the three basic building blocks of IoT. Then the entire world actually is IoT. Understand? Okay. Then what is the processor inside IoT? Right? The popular candidate is a microcontroller. Now you understand microcontroller is very important. Okay, clear. So this is a motivation for you to study this course. So basically, it means microcontroller can serve as a brand. Microcontroller is one of the three basic devices inside any IoT, right? Okay, clear. Then for us to achieve a network sensor, we need a microcontroller. Okay, then we have a lot of network sensor. For us to achieve a network actuator, also you need to have a microcontroller, right? Okay, we have a lot of microcontroller. Okay, and in particular, we can consider machine itself is a mega actuator or mega sensor, or a car, vehicle is a mega sensor, mega actuator. Eventually, the robot is a mega actuator, mega sensor. But inside the robot itself, we can consider it as a IoT or mini version of IoT. From this slide, you see this IoT, IoT in the middle of the slide, right? Okay. So how to achieve IoT in industry? IoT is extremely important. I just play a little bit this video, right?
Many revolutions. But now we're facing the next one, connectivity. But how can a company handle this? What does the industry of the future look like? Our experts have been wrestling with these questions for years. They know that the complete digitalization of the manufacturing industry plays a key role in the process. Why? That's simple. In the future, it will be more important than ever to operate quickly, flexibly, and cost-effectively. Product life cycles are becoming increasingly shorter, while product variants are becoming progressively larger. Just like large volumes, small quantities must be produced economically. Lead times will become shorter, so the delivery must become faster. For companies, this means that in the future, they must align their organization much more rigorously to meet customer needs. This can only be achieved if companies start today to digitize, automate, and above all, interconnect all processes. Not only within the company.
Okay. So it should be good enough. From that video, immediately you understand we are also in the era of Industry 4.0. Now, what is Industry 4.0? The answer is Internet Integrated Manufacturing. I guess some of you may have heard of CIM, Computer Integrated Manufacturing. That is Industry 3.0. When we talk about the Industry 4.0, that is Internet Integrated Manufacturing, right? So without the microcontroller, there's no way for us to achieve Internet Integrated Manufacturing, okay? Then inside the hospital is the same. We have a lot of machine, all right? All these machine could be considered as IoT. And once you see IoT, immediately you must pop up this terminology of a microcontroller, okay? I just play a little bit this video. Right.
We make no secret of the fact that we are determined to head right to the top of medicine. That's what we're doing. This is a beautiful example of it. I saw a machine that I'd seen 7 or 8 years ago in a lab building in Germany at Siemens, which was now a reality. And when somebody explained to me how it was going to be used, what more can you say?
Okay, should be good enough. So you see, in the hospital environment, we also have a lot of machine, right? And each machine inside is IoT. And when all the machine interconnect together, it form another layer of IoT, right? So without the microcontroller, you cannot construct such a machine in the hospital environment. And eventually in future city, we have we call intelligent transportation system or ITC. That intelligent transportation system must leverage on the use of IoT, right? So I just play a little bit this video.
70% of the world's population will be living in cities covering less than 2% of the Earth's surface. Never have cities been so challenged, and the trend continues to grow. This raises many issues: pollution, infrastructure access, traffic congestion, mobility, safety, and the health of residents are only a few examples. The development and combination of new technologies, such as the Internet of Things and artificial intelligence.
Okay, should be going up. So you see IoT. So how to make a future city to be smarter and have a less issue, less problem? Answer is what? AI plus IoT. IoT will produce a big system. With a big system, we have a big data. With a big data, we can achieve a big intelligence. Okay. Then pay attention, big data has nothing to do, it does not mean a big intelligence, right? We still need to transform a big data into big intelligence, okay? So AI is not just big data, okay? So we have big system, big data, big intelligence, okay? Then in agriculture, it's the same, right? In Singapore, I guess this is relevant to us. We may have a vertical farming, right? Then transform agriculture like industry. Okay, I just play a little bit of this video, help you to understand, right, how to construct a big system with the use of a microcontroller, right?
Leafy greens are growing in huge quantities to be sold to local supermarkets and restaurants. This is Aero Farms, a massive indoor vertical farm in Newark, New Jersey.
Our mission is to build farms in cities all over the world so people have access to fresh, great tasting, highly nutritious food.
Crops are stacked more than 30 feet high inside this 30,000 square foot space. They're grown using aeroponic technology.
Typically in indoor growing, the roots sit in water and one tries to oxygenate the water. Our key inventor realized that if we missed nutrition to the root structure, then the roots have a better oxygenation.
AeroFarm says the root misting system allows them to use 95.
Okay, should be going now. So you see, even for vertical farming, because in Singapore we are short of land, right? So we should promote, right, vertical farming, the indoor farming, right? Then control the water supply, control the lighting, control the airflow, right? So immediately you know, right? IoT is very, very important, right? Okay. Then for control system, if you look at the control of the machine, again, so we need to have a microcontroller. And from this picture, you see the PCB, right? Which contains the microcontroller, right? To control the motor. So you need the microcontroller. Okay, I just play a little bit. Then for industrial robot, we can consider robot itself as a mini version of IoT, right? So that in this way, we can ask the robot to undertake automated task, right? Then for humanoid robot, it's the same. Like inside, you have an IoT. So without the IoT, you cannot come up with a solution for the design of such robot, etc. And even for mobile robotics, it's the same. So inside, we have IoT, and IoT include microcontroller, etc. Right? So I just play a little bit this video. Should be good enough just for you to see what do we mean by mobile robotics. Okay, should be good enough. Then, okay, I already mentioned Industry 4.0 means internet integrated manufacturing. And inside Industry 4.0, we must have IoT. Okay, I just play a little bit of this video just for you to see, right? In the production line, so you have a lot of machine. All these machine has to be interconnected together, right? Production.
Welcome to Adept Technology. I would like to introduce you to Adept Technology and show the world of robot vision systems and of course to vision-guided robots. Adept Technology is the leader in the industry in small parts assembly and handling of industrial robots. Nearly 50% of the 3,000 build Adept robot applications use an integrated vision system to ensure quality, flexibility, and a short return on investment. I think you will be surprised to see our robots handling and assembling and inserting parts that you come across in your daily life, like candies, sausages, CDs, all kinds of consumer products.
Okay, should be good enough. Okay, so at least you have an idea about what do we mean by IoT. And the inside IoT, we have a processor, sensor, actuator. Okay, now, okay, for the learning objective. So the philosophy behind the design of this course is to enable you to be the designer of a system which will make use of a microcontroller as a brand, as a machine's brand. Okay, so your purpose is not to become a designer of a microcontroller, is to become a designer of a system which will use a microcontroller as a brand. Okay, understand? This is a main focus of the learning of or study, okay, by you. And the 30% of objective is for you to know how to use the system designed by others in which they are the presence of a microcontroller, right? So you should be able to use IoT, operate IoT system in which they are microcontroller, right? But the primary focus is for you to be able to design machine with a microcontroller inside. Okay, clear? Then how to learn this course? So we have a study of a theoretical part and the hand-on practice of experiment. So this is why each week you are going to spend 2 hours to learn the working principle and 1 hour to do the practice, hand-on practice. Okay, and hopefully through this way of arrangement, you will enjoy your study. Okay, just like I already mentioned, for the assessment, CA 40%, exam 60%. Okay, clear. And also for this course, we have 2 instructors. Okay, I already mentioned. I will help you to study the programming part, the software part of this course. Then Prof. John Han will help you to study the hardware part of this course. Okay, so basically there are 3 modules. One is about the operation of a microcontroller, how to use microcontroller, how to create data flow, right? How to control the data flow. Okay, and for the second part, you are going to study another 2 modules. One is to flow in data, another is to flow out data, right? So if you keep this data flow in mind, then your life is easier. Okay, how to create data flow, how to control data flow, how to flow in data, how to flow out data. That's it. Okay, and the way how to modify the data is not a key focus, but at least you know we are able to modify the data during the flow of the data, right? And the way to modify the data basically is to leverage on the use of primary school mathematics, right? Addition, subtraction, multiplication, I guess all of you know, right? So that's the primary school mathematics. And your focus is to know how to translate primary school mathematics into programming language, right? Okay, that could be a little bit challenge to all of you, right? Okay, so then textbook, etc. learning skill, basically we have a structure, 4 to 5 lab session, right? So you just follow, right? So the practice, okay, practice until 5. So then for each practice, you need to know, okay, how to use integrated development environment, okay, use the software, and focus on data, how to store the data, how to read the data, how to flow the data from one location to another location, or or move data from one location to another location. Okay, how to read in the data, how to write out the data. Focus on data flow, then you will enjoy the practice. Okay, try not to be impressed by the terminology in computer science or electronic engineering, because some technology may not be familiar to you, right? So you just stick to the terminology of a data flow. Everything is a data flow, done already. Okay, very, very simple. Okay, so you read through all these guidelines, should be good enough, right? So then Thursday, I will see you in the lab. Okay, so that's about the introduction. Now we are ready to enter the study of lecture 1, right? Okay, lecture 1. Okay, so now we move on to study lecture 1. For part 1, basically we have 6 lecture. Okay, so if you look at this table of content of this lecture, lecture 1 is just for you to have a little bit understanding about the hardware. Okay, this is like you want to get your driving license. When you want to get your driving license, I guess you need to know a little bit about the vehicle, right? At least about what is the steering wheel, what is the pedal for you to do acceleration, what is the pedal for you to do the deceleration, right? You have acceleration, deceleration, and the brake, the pedal for you to brake the vehicle is deceleration, right? And for the learning of microcontroller as a user, so it's similar skill. You need to also know how to use 3 type of register, basic knowledge. Okay, basically it's a locate, because once we talk about data flow, you need to know, okay, where to store the data. The data cannot flow in the air, right? You cannot say flow inside the air, right? So there must be a location for us to hold the data. And the one particular location for us to hold the data register. This is something new to you. Register is a location for us to hold the data, and is a special type of a memory. Okay, so lecture 2 will help you to know the memory, but lecture 1 is like you just know what is a microcontroller. Okay, it's similar to those of you who want to get the driving license. You need to know what is a vehicle, right? You do not need to know how to design a vehicle. Okay, but at least you need to know how to use a vehicle, right? Okay. And the lecture 3, you see how to represent the data inside the microcontroller, right? Then lecture 4 is for you to know how to create the data flow, how to control the data flow. You use instruction, all right, to manage the data flow. Okay. Lecture 5 is for you to know how to flow in data, how to flow out data, okay, with the use of the software. But in the second part of this course, you will learn the hardware support for you to flow in data, flow out data, hardware support. Okay, here is just purely talk about the use of instruction. Okay, then lecture 6 is for you to know how to modify the data during the flow of the data. But lecture 6 is not our focus, because here we just do very, very simple computation, right? The mathematics behind it is a primary school mathematics, okay? But the focus is on the translation of technical language into programming language, okay? How to do addition, subtraction with the instruction, okay, in programming language, okay? So this is just a scope of a study for part 1, okay? So I can skip all this because just now I already mentioned all this, okay? Okay, this slide also is very important. What is your role? Okay, the objective for you to learn this course is for you to become a user of a microcontroller and the designer of a system in which there is a presence of a microcontroller. So you understand this difference, user of a microcontroller, right? So you are not here to know the knowledge and skill which will enable you to design microcontroller, right? That is beyond your capability, okay? So you put yourself as a user of a microcontroller. It's similar like when you are going to get the driving license, your objective is to become a user of a car. Your objective is not to become a designer of the car, understand? So in that sense, you must know the problem to be solved, okay? Your problem to be solved. Also, you must know the solution, okay, which will solve your problem, okay? So what is the solution? What is your problem? Okay, these are not the focus or scope of this course. That means you have a problem in mind, you have your solution in mind, and your solution is in the form of a technical language. We call it as an algorithm. What do we mean by algorithm? Basically, it's a description of mathematics which could be easily translated into a programming language. So I use your background, right? So define in this way, then it's easier. Okay. So this is your role. You are here to be the user of a microcontroller, right? Okay. And how to learn? This slide is a guideline. Just now I mentioned, keep data flow in mind. Okay. You follow this terminology, then your life is easier, right? Data, keep data in mind, okay? Then automatically you need to know where to store the data, right? So now from this slide, you understand we need the location to hold the data. Location to hold the data is called as a memory. Maybe this is something new to you, right? But not new to student in computer science or electronic engineering, okay? So memory is a physical location for us to hold the data, right? It's like LT. Then what is memory? You see, NT University have a lot of LT. LT is for us to conduct lecture, right? So LT can house student, yes or no? A lot of a class of students can enter LT, and then we conduct the lecture. Same, okay? So then memory must have an address. Memory must have a content, right? Inside the content of memory has by default is data, okay? And since we are able to create, to control the data flow, how to create, how to control data flow, we must write the instruction. When you put the instruction all together, we call them as a programming code. You see the CODE, code, right? Or instruction, a set of instruction. So try to be to be careful. Inside the memory, we may have two types of things. One is data, another may be instruction, okay? But good news to you is the design of microcontroller for ARM Cortex follow the DSP architecture, digital signal processing, okay, architecture, DSP, digital signal processing architecture. So it means we separate, okay, the block of a memory for the storage of a instruction from the block of a memory for the storage of a data. So by looking at the address range, immediately you can guess out whether the content inside the memory is a code or instruction or data, right? So then this picture basically, you see the peripheral SRAM code. SRAM inside is the data. Code means the instruction or program, okay? So try to be slowly, because we will repeat this one, okay, along the study of the lecture, okay? That means by now, pay attention to this slide. If you are comfortable with the terminology in this slide, then done already. Then it will be very easier for you to follow the study of this course, okay? Remember, data flow, memory is a location for us to hold the data. And inside the memory, we can also hold instruction, okay? And another important knowledge, background knowledge for you to pay attention is for each data, that means mathematically, we can talk about this data has an address. This data has a value. This data has a name. For example, 10 could be temperature. Okay, that means this is the value 10, right? The value 10 can be 10 degree of a temperature, right? 10 kilopascal, like a pressure, okay? 10 kilometer per hour, then the name should be velocity. So this is something that, in the textbook we never emphasize, and a lot of you get lost. Just remember this, okay? Memory has an address and the content. Once the data enter a memory, then automatically you can imagine this data has a 3 piece of knowledge. Okay, for those of you, if you want to go into study AI, then people may ask you, what is knowledge? Now you know example of a knowledge, right? So for each data, you have a 3 piece of knowledge. One is a physical value. Second one is a conceptual name or label, right? Then the third one is data value, data label, data name. Okay, so it is just these two. Okay, so address. Third one is address. Okay, so for each data, you have a 3 piece of knowledge. Address of the data, value, physical value of the data, conceptual meaning of the data. Conceptual meaning of the data means a label or name. Understand? Physical value, conceptual meaning, and the address of the data. So if you want to move on to study AI, remember this, then you understand what do we mean by knowledge. Okay, clear? So this slide is conceptually is very simple because, but since you do not have a computer science background, maybe this slide is totally new to you, but it is extremely important. If you forget about all this data, memory, address, value, label, name, instruction, then you get lost already. Okay, clear? Okay, so pay attention in case if you still can capture the meaning of data, address, value, label, okay, and instruction code. Then, okay, do a little bit of revision, right, about this slide. So these are the definition. And in terms of skill, just now I already mentioned how to drive a car. Very simple. You just need to know how to operate steering wheel, how to operate acceleration pedal, how to operate braking pedal or deceleration pedal. Let's say just 3 things or 3 actions. But you cannot say, I know how to operate these 3 actions, then I'm able to drive to drive a car to go to any location. Actually, it's no, right? It depends whether you drive a car from NTU to NUS, right? The skill of driving, operating the steering wheel, acceleration pedal, braking pedal is not good enough. You still need to have a perception, decision making, right? So same for the use of a microcontroller, you just need to have a 3 basic skills. Done already. Know how to configure control register. Know how to monitor status register. Know how to read and write data to and from data register. That's it. That means pay attention to control register, status register, data register. Okay. But this skill is important for you to remember for the study of the second part of this course. For the first part of this course, you just pay attention to register. Register is a special type of memory, or is a memory with a high speed. Okay, it's very fast. Okay, it's the fastest memory in the whole world. Okay, very fast, and it's very expensive. So this is why we do not have many register, because it's a cost. Okay, it's very fast, expensive. Okay, then we do not have too many. Okay, so these are basic skill. Then at the bottom, you see the instruction for you to operate this register is the same. It's very simple. You just use one of these 3 instructions: move, or load, or store. Okay, the physical meaning is MOV means move, move from one location to another location. Then you see data flow. Load, right? Load something from lorry into your house. That means also load from one location to another location. Store is the same. Store from the living room, something from living room to the storeroom, right? It's also move something from one location to another location. Just use one of these three, good enough already, right? So that is way to create a data flow. Okay, very, very simple in terms of skill. But challenge is when to use control register, when to use a status register, when to use a data register. That need you to build up experience. This is exactly like learn how to drive a car, right? To operate steering wheel, to accelerate, to brake is very easier. Learn how to combine these three skills to drive a car from NTU to go to AUS. That require experience, right? You cannot say, I know how to operate steering wheel, I know how to press acceleration pedal, I know how to press braking pedal, then I know how to drive a car from NTU to AUS. You cannot say that, right? That depends on experience. Okay, clear. So in terms of basic skill, very simple. Then how to use it? This is why you need to have a practice, right? Similar to the case when you want to get your driving license. Understand? Okay. So that's about the, okay, this is the background knowledge for you to remember. Now we enter the study of lecture one. Lecture one basically is for you to know what is a microcontroller, right? Okay. So, and the microcontroller serve as a brand. Then just remember, ask yourself, what is your brand? I guess all of you know, I guess all of you have a brand now, right? Then ask yourself, what is your brand? Okay. And how to operate your brand, okay? Then are we able to invent? Our brand is a biological brand, yes or no? Can we invent digital brand or digital computer, right? So that we use them to serve as a brand for machine, okay? And for this course, we use ARM Cortex microcontroller as an example. Okay, now you see this ARM, okay? ARM basically is a trademark, all right, of a company called ARM. Okay, it's a trademark. It's like Intel microprocessor, Intel processor, okay, or Motorola microcontroller, something like that. Okay, and how to operate microcontroller. Now you see we have the integrated development environment, IDE. This is a software interface for you to operate or program microcontroller or monitor the running of a microcontroller, right? So it's like inside the car, you have a dashboard, right? Control board, and it will visualize the speed and the amount of fuel inside the tank, whatever, right? Okay, so it's the same, okay? So to use microcontroller, we have an IDE. Okay, this will be the key takeaway from today's study, okay? First, pay attention to the brand. So now look at this conversation now, right? If a person asks another person about this simple calculation of 6 plus 9 is equal to what, right? Then pay attention to mental activity inside person B, right? So at least you know person B must, understand number 6, understand number 9, understand addition, right? And is capable to undertake addition of 6 plus 9. And it will generate value data 15. Then synthesize, right, answer. Then use the sentence to control the muscle of the speech to produce the sound as an output and which will respond to person A. So you see a lot of mental activity occur inside person B, right? Then you ask yourself, if let's say we want to replace person B by a robot, okay, then how are you going to design such a robot which could replace person B? Immediately you know, right? This robot must have a microcontroller. Otherwise, it is impossible, right, to achieve this sequence of mental activity. Okay. how come we are able to do all this mental activity? Answer is because our brain is I must say that it's a general purpose organ, right? Because in the medical textbook, they always make you believe that this is a specific purpose organ, right? Certain area for vision, certain area for audition, etc. Certain area for the coordination of motion. Actually, we have an example which violate this theory of specific allocation of a brain. Okay, so we have people even without the cerebellum. Okay, and this person still have a normal life. Okay, we also have a people and his brain is only about 10% of the brain of a normal person. That means that the person only with 10% of the brain of of a normal individual, but this person still have a normal life. Okay, so this means what? Our brain is a general purpose organ. Okay, we can dynamically allocate the area of the brain to handle the data flow or data computation. Okay, it's just for you to know. By this, you pay attention to these three terminology laws. Cerebrum is for high-level computation. Okay, so this may correspond to high-end digital computer. And then you see this cerebellum. Cerebellum actually is correspond to microcontroller. Okay, cerebellum is coordinate the motion, right? Interface with the sensor, interface with the muscle or actuator. Okay, it's very much like a microcontroller. But pay attention to another one, which is a middle brain. You see, that is a control unit. Is surprisingly the invention of today's digital computer more or less follow this architecture. We have a control unit, then we have a CPU. CPU can serve as a cerebellum or cerebrum. Okay, very interesting. Okay, so this is just summary about what our brain and the mind can do. Okay, for those of you, if you want to venture into the study of AI, pay attention this misconception. Okay, intelligence is generated by mind. It is not generated by brain. It is totally wrong to believe that the brain produces intelligence. Wrong. Okay. So after study of this course, you will understand why. Okay. So, and the mind dominate brain together, they will achieve this to undertake this sequence of mental activity. Okay, that means the mind leverage on the use of a brain. Okay, will be able to achieve this sequence of mental activity. Keep this conclusion in mind, and when you want to venture into study of the AI, otherwise you will get lost already. Okay, so and we have plenty evidence. Okay, in other domain. Okay, and convince you about the relationship between intelligence and the mind, right? So intelligence has no direct relationship with the brain. Okay, and we can also have a mind without the brain. That is a very strong statement. Mind without the brain. Understand? Okay, but that is beyond, because such a discussion is beyond this course. But it's just for you to know. Okay, associate intelligence with mind, right? That's it. Okay, if let's say we want to replace person B or A by a robot, okay, then in this scenario, immediately you understand, okay, robot must have a mental capability which will be enabled by the brain and the mind together, okay? And then now you see, today we just use digital computer to serve as a brain of a robot. Then what is the digital computer? This is the blueprint of today's digital computer. Okay, I just quickly showing you. You just pay attention to control unit. Control unit, you remember, is like our midbrain. Okay, then we have a ALU. You see, ALU is like a cerebrum and cerebellum. right? ALU. And we also have a memory. That means ALU together with memory, memory unit, okay? Then we also have an input unit, output unit, okay? So this is a blueprint of microcontroller, okay? And inside we have all these control line, signal line, data line. I guess later on you will appear, okay? Yeah, I just continue. Okay, now you see we have at the address bus. Okay, this is another terminology which is new to you. Bus does not mean transportation bus. Bus means a set of a line which allow or which enable the flow of a byte, 1 byte, 2 byte, 4 byte, or 8 byte. If the set of a line allows the flow of 1 byte, 1 byte means 8 line or 8 bit, then we call this as an 8-bit microcontroller. If the bus has a 16 line, which allow the flow of 2 byte, then we call it as a 16-bit microcontroller. Okay, for ARM Cortex, the bus allows the flow in, flow out of 4 byte, 32 line, 32 bit. So then we call ARM Cortex as a 32-bit microcontroller. Once you see this terminology, 32-bit microcontroller, it means, okay, at each cycle, we can flow in, flow out 4 byte, something like that. Okay, so this is a blueprint of microcontroller, but you do not need to remember this. Okay, you just see a similarity between digital microprocessor and biological brain. Good enough already. It's very interesting, right? Okay, something like that. Then with the electronic brain and mind, we should be able to enable, right, today's machine to achieve similar mental behavior, okay, which as a human mental capability, okay? So you will see. And the last few lines basically highlight to you the scope of a study of AI, right? To learn human language, okay? Machine language, need to learn new knowledge and new skill. And this will be the scope of the study of AI, right? Or the man, right? Something like that, okay? Then you may want to know who are the inventor of the design of a digital computer. So basically, today's computer architecture are based on the invention made by John von Neumann, right? So you see, he's a mathematician. So, and the improved version is called as a Harvard architecture, but that version basically is a variation of John von Neumann's architecture, okay? So just remember this person because today's digital computer has benefited from his invention. Okay. On top of that, also you need to know, right, who is Alan Turing and George Boole, right? Because when you talk about Boolean logic, okay, so that is a development of mathematics made by George Boole. Okay, and Alan Turing basically he pushed forward the terminology of a thinking machine. And he also has made a contribution to the development of AI, etc. Right? Okay, yeah. And then this is a blueprint of architecture invented by Neumann. Right? So from here, you see we have ALU, computational unit, and the storage unit. So they are separated. Okay, but for DSP Harvard architecture, you just do a little bit of improvement, right? For the storage unit, it is split into two. One is for the storage of data, another is for the storage of a program. But that kind of improvement is trivial. It's not very, very critical. Okay, clear. So then, so you see for Van Neumann, okay, this is another way to highlight the detail of Van Neumann architecture. Okay. So you see we have a central processing unit, then we have main memory. And inside the main memory, we can still divide it into two segments. one for data, one for program instruction. Okay, so these are the basic architecture, right? Okay, so that's about the biological brain in comparison with digital brain. Okay, you see a little bit of similarity. And the inventor of digital computer, I just quickly go through. Okay, so this person has invented a mechanically operated computer, but obviously today we never use it, right? But at least he laid the foundation for people to venture into the design of electronically operated computer. Okay, so and this person contribute to Boolean logic. Basically, is to use 0101 to represent all kinds of number, right? So it's a data system, okay? Boolean logic and plus the binary data system, binary 0101, okay? So it's quite important, all right? And this person you need to remember, right? And his invention are the foundation of today's digital computer, right? So for today's digital computer, the basic blueprint more or less follow his invention, right? Okay, clear. And then another thing you need to remember, institution is a Bell Lab. This lab is very, very important, all right? The invention of transistor was made in Bell Lab. Invention of internet, the ARPANET was made in this lab. And the invention of a C programming language was made in this lab. Because C programming language is very important. And you may heard of C, C++, C#, Java, Python, MATLAB, and all these programming language can trace back to C programming language. Even for operating system, you may heard of Unix operating system. So Unix operating system are being written with the use of C programming language. Okay, you see Unix operating system was also made in Bell Lab. Okay, so remember this lab is extremely important because of huge contribution made by this lab. Okay, clear. Then for personal computer, you need to know IBM personal computer, and inside you have a DOS operating system, Windows operating system. Okay, Microsoft. Okay, and another type of personal computer should be Macintosh, right? And from Apple computer, right? Okay, so all day we have this called Macintosh, right? Okay, so and once you heard of this terminology of personal computer, you may ask yourself, right? When will we see the emergence of a personal robot? Right? How to transform a personal computer into personal robot? Basically, is to make a personal computer to grow two legs, to grow two arms, and to grow one hand. Then you will see a personal robot. Okay, so that is an evolution in terms of a body of a personal computer. I mean, today's personal computer is a simplified version of the head. Okay, and because all of you are from mechanical engineering school, and it should be trivial for you to extend personal computer into the version with a body, with a leg, with an arm, with a hand, something like that, right? Okay, once you do that, then we have a personal robot. Okay, something like that. Okay, so that's about the inventor, the important person for you to remember. Okay, then we zoom in into the hardware which will support us to learn this course. Okay, so we use ARM Cortex-M4, right, to support your study, to support your hand-on practice. Then you need to know, right, beyond ARM Cortex-M4, what are other the sister brother of ARM Cortex-M4? Okay, so this is why you need to know the family of ARM microprocessor. Okay, So ARM is a trademark, okay, so you know it's a company founded in the UK, and so far is the most popular microcontroller in the whole world because people use it to design all kinds of a machine, right? Consumer product, etc. Consumer electronic product in the whole world, okay? Basically, this family has three type of a microprocessor. One we call is a classic one, embedded one, and application incentive one. Okay, embedded one basically is a microcontroller, right? Classic one is a basic version for low cost, etc. Then for application which require little bit of computational power, then is application version. Okay, for us, we just focus on embedded version of microcontroller, right? Okay, if you need to undertake intensive data processing, then you need to use other type of digital computer, right? Okay, so basically you have a three family, right? M version is M means microcontroller. R means it's a real-time critical, I guess. Yeah, it's a real-time, right? A means application is a high performance data processing. Okay, basically, roughly you can think about these three versions. One is a time critical, another is for the control or IoT, right? To construct a big system. Okay, it serves as a node, okay, to connect sensor actuator. That is the M version. Time critical for some application in military, right? So when you take action, your delay has to be as short as possible, right? Even for network communication, the delay of data communication also critical, right? Okay, then for application critical, okay, platform, because a lot of application will involve a lot of data, right? So then the microcontroller must have a powerful capability to handle data processing, data flow, etc. Okay, clear. Then for us, we just focus on the M series, but regardless of which series, but the microprocessor, the basic architecture are the same. Okay, so this is showing you the foundation. That means the foundation of these three series of member inside the family are the same. Okay, it's only configuration are different. Okay, so the basic architecture are more or less the same. So this showing you the evolution of the basic architecture. Okay, so we may heard of ARM v7, v9, and today you also heard of Cortex X2, and maybe something new thing come out, right? It is keep evolving. Okay, you should not worry about this. Okay, so you just need, because at the bottom, the hardware architecture may change, but your programming skill remains the same. Nothing change. Okay, because the language more or less is a static. It's like English language. Once you know English language, okay, more or less stable, right? You cannot say 10 years ago English language is quite different from English language in today's situation. No such sense, right? Okay, so it's the same. For our focus is on the programming, how to create, control data flow, right? So you just need to know a little bit of the hardware. Hardware may evolve. It's same like a car, right? Once you get your driving license, even we have a newer version of a vehicle or car, we never ask you to to go back to the driving school, get a new driving license. Okay, no such sense, right? Once you have a driving license, you can drive any old car, new car, whatever, right? Okay, same situation, you should not worry about it. Okay, so this is a evolution of the architecture at the lowest level, right? So you keep improving. It's like the car, right? You have a newer version of the vehicle, but your driving license is still the same, right? Never change. Okay, clear. Then for us, our focus is on M series. Now you see today we have M7, but for this course we use M4, right? Okay, M4 is an older version, but because our purpose is know how to gain the skill of making use of microcontroller, they should not worry about the hardware evolution in terms of performance, etc. Okay, so then, okay, you look at the architecture, is M4, more or less similar, right? It's just incremental improvement. There's no fundamental change in terms of the hardware. Okay, clear? So you see Cortex M7, but this is zoom enlarge the view, right? So you do a comparison, not much difference, right? Maybe you have a more hardware support, but conceptually more or less the same. Okay, you should not worry. Okay, so this microprocessor has been widely used in the whole world, most popular microprocessor. Okay, so this will give you motivation, all right, to study well this course, all right? Okay, and for the microprocessor was developed by ARM. Okay, this limited company, but other company has come out the development kit, right? So create the motherboard, okay, which include the Cortex M4, right, and also provides the IDE and make your development work much easier. Okay. Then for our experiment, we will use Texas Instruments development environment, right? It's the hardware, software, okay, etc. And on top of Texas Instrument, we may have other supplier of the hardware and the software, etc. Okay, it's just for you to know. Okay, so this will be the version for you to use for the practice. Okay, so this is from Texas Instrument. Okay, so just for you to know, you can go to the web page. You can download the learning project 0. Okay, so this you can download free from Texas Instrument website. Okay, if you want to play, it's up to you. Okay, or you wait for the lab session in the lab. It's okay because we have plenty time for you to do the practice. You should not worry, no need to rush. Okay, we can also extend the Cortex M4 to incorporate vision system, speech system. So in the lab, we also add in a little bit the simple sensor and the display device. Display can be the lighting device, right? Or the speaker, simple, the buzzer, that's a speaker, simple one. Okay, and also can capture input through the switch. Switch is also a way for us to input data to microcontroller or the button. Button switch basically is similar device, right? Since our intention is not just for you to to learn how to interface, how to construct IoT, right? Because the focus of the study in this course is to know how to use microcontroller, right? So we showing you a little bit of simple example of how to read in data, how to output data, good enough already. And we have a whole range of input device, whole range of output device. Like you just imagine, okay, good enough already. Okay, so then vision is very powerful, the most powerful, right? Most complicated input module, right? Even for human being, right? Our vision system will occupy #1 position in our mind. Okay, for those of you, if you want to study AI, you must know, right? So inside AI, we have a lot of module, and the module #1 should be vision system. Module #2 should be speech system, right? You see, the ARM Cortex can also interface with microphone, right, to form a speech system. This is the hardware support to the #2 module inside any AI system. Okay, so once you know the hardware support for #1, #2 module inside AI, good enough already, then you see this course is extremely important if you want to know what is AI. Okay, clear? So on top of that, we also have a general purpose development environment, CARE. This is not depends on any company which supplies the hardware. Okay, but of course, the hardware supplier may have their own version of development tool. But here you can use this general purpose tool, like CARE, right? You can download from this website, right? On top of CARE, you have Energia, right? Okay, and the Chord Composer Studio IDE from Texas Instruments. The third one is from Texas Instruments, right? They call CCS. We do not use it. In our lab, I guess we use CARE, right? KEIL, okay? It's the first one. So it's a general purpose. Okay, it's just for you to know. And for the Cortex M4, that means the M series, just now I already mentioned, is a 32-bit microcontroller. Okay, just need to know all these things. 32-bit means at the one time you can flow in, flow out. Internally flow in, flow out. 4 byte. 1 byte has an 8-bit. Okay, this is also something new to you. Okay. 1 bit is one series of 0101. And for you to communicate 1 bit, you need to have the support 1 physical line, 1 cable, 1 LAN. Okay. If we want to communicate A bit, then we need the A LAN, right? Or eventually, that means 1 LAN, then you have a series of communicate 1 bit, another bit is a shift register, okay, to do the shifting, okay? And you put the AP together. That is the smallest unit of data in digital computer. Pay attention. If people ask you what is the smallest unit of data inside the computer, answer is 1 byte, not the 1 bit. Understand? What is the smallest one unit of data? Is 1 byte, not the 1 bit. Okay, so 1 byte has an 8 bit, then 32 bit means 4 byte. So that is intended, but pay attention. For between microcontroller and the external device, we have a hardware support for the data communication. This hardware support, we call it as a port. Each port can only support the communication of 8 bit, just 1 byte. Okay, in the second part of this study, you will encounter this content. By now, in your mind, just remember, okay, internally 32-bit at the 1 cycle, flow in, flow out, internally 4 byte. But between microcontroller and the external device, okay, the one-time maximum number of, at the one time, maximum number of a bit is 8 bit. If you have a more than 8 bit, then you have a multiple cycle, right? 1 byte, second byte, third byte, etc. Series of a byte. And then eventually, in order to save money, just save the investment, maybe we only have a single line, single cable. Then in this case, we must convert a series of byte into series of bit. Okay, keep this in mind. Okay, then you will know, okay, little bit of complexity when you operate the hardware. Okay, it's because of this. Okay, if let's say we have a 32-bit output, 32-bit input, then your life is easier, right? No need to worry about this conversion from byte into the bit. Okay, because of this conversion of a byte to bit, because we want to save the cost. Okay, otherwise you will be costly. Okay, clear? Then it creates a little bit of complication for you to operate microcontroller. Okay, keep this in mind. Good enough already. Okay, and okay, then this is a architecture of Cortex M4. Okay, internally you see, when you see the number, okay, when we have a 32-bit, you mathematically is a vector. Vector has 32 element, and in MATLAB, the index always vary from 1 to 32. But in C programming language, in engineering, convention is the index always vary from 0 to the capability, maximum capability -1. If let's say we have a 32-bit, 32 minus 1, 8-bit, then A minus 1. Okay, now you see the A is a vector. That means you have this number of a bit, but the index vary from 0 to 31 because we have a 32-bit. Okay, and the data is the same. D, you see, D is a value of a data. Then you have a value of an address. Okay, so A means a value of an address. Okay, D here means a value of a data. O are 32-bit. Tree as a vector with a 32 value. Index vary from 0 to 31. Done already. Okay. Then what else? This is a inside. Okay. Everything is a 32-bit. Okay. Inside the bus. And the microcontroller can be configured into different mode. But for us, we only pay attention to the user mode. The rest, you do not need to pay attention, okay? Because you are not from electronic engineering, you are not from computer science, okay? You are from mechanical engineering school. Then your role is to be a user of a microcontroller. Just pay attention to the user mode. The rest, just ignore them, okay? So in the user mode, just pay attention to here. So this is a working space, working memory. And the working memory, we call them as a register. Now you see you have a register R0 all the way to R15. So it means what? You have a 16 working memory, right? Each register has a 32-bit, understand? That means each register can store 4 bytes, okay? And the register 13, 14, 15, you cannot use it because they have a dedicated function. SP means a stack pointer. This also is a new concept to you. This is something useful when you do the multitasking. That means we suspend one application. Okay, then the context of a working memory must store into a memory. And the temporary storage memory. Then what is the first address of this storage memory? This address is stored inside R15. Okay, it is this operation. PC 15, you must know, is a program counter. Basically, it points to the it holds the address from which we can retrieve the next instruction to be executed. And here you understand how computer can execute program one by one. It's just to read the data or read the value from PC from the register 15 and treat the value as an address, then from which we retrieve the instruction or the code, then perform the instruction, okay? Once you retrieve one instruction from PC register, then this value will increment by 1. When it increment by 1 means what? It points to the next instruction. Okay, that means now we undertake a current instruction, then the PC already points to the next instruction. Then we repeat this operation, then whole program will be automatically performed by the hardware. Okay, so you understand what is a PC, then you know how the program is being executed step by step. Okay, this is also something new to you. Then you just to remember like this. Okay, conceptually very simple. Okay, LR, the register 14 is also a concept useful for you to know, and you do not need to operate, but at least you know there's a hardware support for you to call a function. For those of you, if you have a programming experience, you know you can call a function. When the function finish, you can always come back to the location where you call the function. How come you know to come back to the right place? Answer is what? When you call a function, you jump to a new location in which you find the storage of that function. Once you go there, and you will leave the current location, the current address will be stored inside the LR register. Okay, once you finish execution of the function, then the PC will just copy the value from LR into PC so that then you continue to execute your previous program. Understand? So you have a main program, then you have a function, right? At the one point, you call this function. When this function finish, you can always come back to the same location inside the main program. How come you can come back to the same location inside the main program? Because the location at which you go to the function has been memorized by the link register. Okay, so this is just for you to know the hardware support, okay, to the function code. Okay, then you should not worry. All right, I call a function for sure and be able to come back to the main program. Okay, clear. So this just help you to understand now. Okay, the hardware support to such operation. Okay, and then okay, this is just configuration of the foundation inside the call that M series. So once you have an M series, basically it means it has a low is a profile configuration. This just for you to know you do not need to do anything there. Okay, so this help you to understand with the same architecture, we can configure it into M series, R series, or A series. How come we can configure them into M series, R series, A series? Answer is what? We just load a profile configuration file, right? Then done already. Okay, just for you to know. Okay, this is something. Another thing for you to know is ARM Cortex is a high-speed microcontroller because internally he has two data bus or two address bus. Yeah, two address bus. It's like in Singapore, we have a PIE, we have a AYE, then make the traffic from the east, between east and the west, okay, more efficient, right? We can handle more higher volume of the traffic because of a two highway. This is just for you to think, right? Same. So we have a two address bus, okay, go to the same memory location. That means we can achieve a higher volume of data flow, okay? But this knowledge is very important for you to understand when you study the second part of this course. For each register, we have two address. Why? You can say, how come I have two address? Answer is what? Because we have a two highway, two address bus. Okay, that means we double the register. Okay, so that means a double capability for same register. Actually, you have a two. It's like a twin. Okay, so then we are because one address bus is being used by one register, then you can use another address bus for another register, right? Then you can do little bit of parallelism, right? two address can flow out at the same time. You see, you will shorten the speed by half. This just for you to know, but in the software side, you just pay attention to address. That means for each register, actually you have a two. Then how are you going to identify which one? Just through address. Then you will see there are two address for one type of register. Okay, it's because of this hardware support. Okay, clear. So and you also have the interrupt and fast interrupt. Okay, interrupt also is a new concept to you. Actually, all of you are familiar with the interrupt already. For human being, okay, I guess all of you have experience of feel hungry, true or not? I guess all of you, I do not believe none of you have this feeling of being hungry. Then what do you mean by hungry? Actually, it's interrupt. Your stomach send the interrupt to your brain. Tell your brain that your stomach is empty. This is why you feel hungry. That once your brain receive this interrupt, then you go to a restaurant, you eat, right? And your brain pay attention, automatically erase this interrupt. Then your brain will no more feel hungry. Understand this operation inside your body. Then you ask yourself, well, what happens if your brain, for whatever reason, has forgotten to erase after eating in a restaurant and forget to erase the interrupt associated with being hungry? Consequence is what? You keep eating until you die. Yes or no? So the same thing will happen with microcontroller. This is something for you to remember. Okay. So if let's say interrupt means it's internally generated signal which tell your brain something happened, whether it's empty, full, or whatever, 40, whatever. Okay. If your brain or your mind, the microcontroller's program will handle or response to this interrupt internal signal, always remember to clear it after the service, after the response to the interrupt. Otherwise, it will keep respond to the interrupt. So it's the same. Okay, after eating, your brain, your mind automatically clear this signal, no more hungry, right? But you just imagine consequence. If your mind never erase this signal, you will keep eating until you die. Understand? So same thing will happen with the microcontroller. If the mind of the microcontroller never erase, okay, the interrupt after responding to the interrupt. Okay, keep this in mind. Good enough already. Okay, this is something for you to know. Fast interrupt, easy to understand. It has a higher priority, right? And then you also have the soft interrupt, etc. Right? Okay. So this is telling you the two buses, right? Okay, to speed up the communication. And this is more important. We have IDE. You see, use a computer, then through interface. You can write the program inside your computer, then you download. And this is also very important. Some students forget to do it. Whatever you modify inside your computer, if you do not do the download, nothing happens inside the microcontroller. And some students always say, I have already modified, I execute it, how come nothing happened? Answer is what? You have forgotten to download, modify the version to the microcontroller again. Okay, always remember, whatever you modify, recompile it, download it, then execute it. If you just modify, then you execute, nothing happen. All right, because you have not yet compiled it, you have not yet downloaded it into microcontroller. Okay, so once you see this join, remember that you cannot say the host computer should be smart enough, whatever I modify, then automatically update the microcontroller. We have not yet reached that stage, right? This could be a research topic for AI in future, right? In future, maybe in real time, when you modify your program, then behind the computer is smart enough, right? Automatically combine it and download it, okay? But today we have not yet reached there. We reached that level of intelligence. Okay, then we leverage on your intelligence. Understand? Okay, so remember to do this. Otherwise, you will waste a lot of time to ask questions. How come no response? Nothing happens, right? Okay, clear. So now for IDE, you need to, through the practice, let you know how to use it, a lot of help file, etc. It's not by teaching that you understand how to use IDE. You need a practice, okay? So IDE basically is allow you to translate your solution into program. IDE also allow you to visualize the data flow and also to know where the data store, right? How the data will modify, go to a new location. So keep data flow in mind, okay? So to achieve data flow, you must flow data from one location to another location, right? So the location or memory of a data, right? So now you see, conceptually, we code data. Physically is memory, right? Keep these two terminology in mind. So memory has an address, memory has a content, right? But for data, always remember, has a three pieces of knowledge. Data has an address because he will store inside the memory. The memory has an address, then data has an address. So data has a value because memory has a content, right? And on top of that, data has a conceptual meaning, which is a name or label, right? When you write a program, you allocate memory, you use conceptual label, conceptual name. Keep this in mind, then you will feel comfortable about the programming. Otherwise, you get lost, okay? When you see data, three knowledge, data address, data value, data label, data name, right? Okay, clear. So your role is a user. You know your problem, you know your solution, then you translate your solution into program. Then you use IDE, right? That is your role, okay? Then how to translate your solution into a program? Then you must first describe your solution in mathematics. Once in mathematics, then you must describe a data flow. Now you see this diagram. Basically, we call it in computer science, we call it as a block diagram. Yes, they call block diagram, but this is not so meaningful. You treat it as a data flow diagram, then you feel comfortable. Okay, it's like a control theory. Control theory, when you study control theory, I do not know how many of you have done the study of control theory. We also have this block diagram, yes or no? Block diagram. Okay. No, in computer science, this we call flow chart. Okay. In computer science, they call it flow chart. Okay, but they miss out the one thing. Is a data flow chart. Okay. Or you call data flow diagram. Then it's more meaningful. Flow chart. Flow of what? Because we may talk about flow of water, right? Flow of material, flow of energy, right? So it's a data flow diagram, okay? But in control theory, block diagram should be signal flow diagram. Understand? Signal flow diagram, control theory, data flow diagram in the study of a microcontroller or programming language, okay? So treat this as a data flow diagram. You see it's a conditional. If have this signal, if data is like this, then I flow to the left-hand side. Otherwise, I flow to the right-hand side, okay? Treat this as a flow. You may have a parallel flow and the sequential flow, conditional flow. Very simple, conceptually very simple. Remember, data flow, data flow, data flow. Then, okay, good enough already, okay? So with IDE, you can implement it quite easily, okay? And this is a real example for you to translate the application of electric toaster, okay, into the data flow, okay? So you see the computational flow. The toaster, you know, you place a bread inside, you press the on button, right? Then the heater start to increase the temperature. Then the bread will start to receive the thermal energy, then change the color, whatever, right? Okay, so you see input from switch, start, cook, and then there's a loop. So you see the computational flow diagram. Hook means you press, you on or turn on the electric toaster. Output heat is on, then input toast temperature. And if the temperature is lower than the desired value, then continue, right? Continue to the heat. If the temperature is under control of the temperature, if the toast desired temperature, it means this, right? Then stop, okay, then output the toast, right? Okay, the bread. So you see the data flow sequence, okay? Then once you have this data flow, then you can translate into a program already, use programming language. So this activity, we call it programming. Programming basically is a translation. You have a solution in mind. Okay, you describe your solution in mathematics. Okay, mathematics is very simple. If the temperature higher than certain degree, stop. If it's less than certain degree, continue to heat it. Very simple mathematics, right? Okay, then you draw this data flow diagram. Okay, then you translate this data flow diagram into program. You see input port B basically to read temperature, right? Then output something to port D is to trigger, okay, whether you continue the heater or just stop the heater, right? Something like that. But in the part 2, then you will learn. At least from here, you know port A, port D, port B is for you to interface with the sensor actuator. You keep this idea in mind, good enough already, right? So you write your program which can control sensor, control actuator. Heater is actuator, yes or no? Emit the heat is actuator. Sensor means what? Temperature, right? Temperature is a sensor. From this example, you see, we can read in sensory data, output control signal, on or off, right? And the control signal go to actuator, right? So this is a very, very simple example. And then for IDE, they will give you this user interface, which allow you to visualize the data inside the register, data inside the memory, and also visualize your program flow, computational flow. Computational flow will generate data flow, right? And also the translation of a human readable program into machine readable program. So on top, when you see all this binary number, okay, that is computer readable. You cannot not understand, right? But human readable is below, you can read. So through practice, you will gain exposure to this type of visualization. Okay, clear. So that's all for today's study. So the key takeaway is for you to know why to study this course. Answer is what? Machine need the brain, all right? The whole world is IoT. Without the processor, there's no IoT, right? Two motivation, okay? And then what is the brain? Okay, you can do comparison between digital brain and the biological brain, okay? You just understand the concept, no need to know how to design it, good enough, all right? Okay, then some name for you to remember who have invented a different type of a computer, right? And the architecture, etc. Right? Okay. And our focus is on the use of ARM Cortex-M4 microcontroller to support your study and the learning of the basic knowledge and skill, right? And the key terminology for you to remember because of your background, because you are not from electronic engineering, you are not from computer science engineering, then remember data flow, right? So use this terminology to guide your study, right? So microcontroller basically is a device for you to create, to control data flow, and also to modify the value of the data during the flow of the data. That's it, 3 actions to create, to control, to modify, right? Data flow, right? Okay. And the good news to you is all the development hardware will give you integrated development environment. Then you need to learn how to use this IDE to translate your solution, your algorithm into program, okay, which could be run by Cortex-M4 or microcontroller, right? The IDE will help you to visualize the data, visualize the value inside the memory, etc. Okay, so that's all about today's study. Any question for those who are present here? Okay, since you are here, you can turn on your microphone if you want to ask question, right? We still have a few minutes for Q&A. Okay, if no question, then see you on Thursday, right? I guess, all right, or in this week. Okay, see you on Thursday. Bye-bye.
Thank you, Prof.
Okay, thank you.